So welcome everybody to the topical meeting today. Daniel Allan is going to be talking a little bit about tiled. I assume everybody has seen the abstract. It's a rather fascinating project. I can't remember exactly when it was I got interested in it, but I've now seen a couple of talks and some demo work, and I think it's got a real intersection with some of the work that we do, especially with cataloging and data delivery a la ServiceX, and some of the open data stuff that we've been looking at more recently. I think it was Thomas Caswell actually who first pointed this work out to me. So Daniel, you're at BNL at Brookhaven National Lab, and just before you get started, I wonder if you could just give like a 2-minute introduction of your background and then just slide right into your slides. And as long as you're okay with it, people can sort of make short interruptions for clarifications at any point, and then certainly during the tutorial. Is that fine with you?
Yeah, absolutely. I think that's
perfect.
That's how this is going to work best. So please do err on the side of interrupting, and feel free to try and re-steer me. A live demo is more fun when you can sort of make it up as you go. Sure. So about me, I started at Brookhaven National Lab coming out of a soft condensed matter experimental physics PhD program at Johns Hopkins graduated in 2015. Did a postdoc for about 6 months in what was really a scientific software role at the National Synchrotron Light Source 2 at BNL. And after 6 months, I became a staff position working with Thomas Caswell and several others. Over the years, we've built up a software ecosystem that I'll describe in my slides, really running the gamut of the full stack from low-level hardware protocol control stuff up to experiment orchestration and data management, data access. I spent a lot of time in graduate school contributing to the PyData stack, learned how to use Git by trying to contribute to pandas, and that kind of steered me from my experimental science roots into a more scientific software role, which is where I live now. So I think with that, I'll get into the slides. So I work in the Data Science and Systems Integration Program, newly founded in March, I think, at the National Synchrotron Light Source 2. That's a user facility. So we do some of our own research at NSLS2, but our primary role is a sort of customer service role where scientists will come in person or ship us their samples remotely, do an experiment for a couple days or a week, and then go home with their data, or go home and then remotely access their data, as the case may be. So a wide variety of different sciences happening there. I'm presenting this library that is part of a larger effort that we call Blue Sky, a mini ecosystem of software designed to make it easy for synchrotron scientists to leverage the SciPy ecosystem in particular and open source scientific software in general. There are many facilities that have bought onto this to some degree listed here. And this particular work on data access has had the involvement of Thomas Caswell, Marcus Hanwell, who we recently hired from Kitware, Garrett Bischoff, and Stuart Campbell, who's the group lead. Also funded on a grant focusing on applying AI ML to synchrotron science. Dylan McReynolds from the Advanced Light Source in Berkeley is on this call right now, and he has also had a lot to do with this work. So Blue Sky, multi-facility collaboration started at where I'm at, NSLS2. Other DOE light sources have bought onto this project, and we've had some adoption at international facilities as well. So this is becoming a little corner of the SciPy ecosystem focused on user facilities and in particular synchrotrons. We have some university research groups who found these tools scaled down as well as up, which is something that's very important to us. There's an electrical engineering group and a chemistry group who are using this for basically lab bench science. And then like any open source project, you never really know who is using your tools. A couple months ago, some people who do infrared ground-based surveys turned up with some questions about Blue Sky. So it's a nice little proper open source community nowadays. Organizing all of these people and their various requirements and needs is obviously a much harder problem than any of the technical problems that we have. I'm sure that's familiar to this group. And so our ethos, which I imagine that IRIS-HEP shares, is trying to find ways to collaborate but specialize, right? People are incentivized to do something no one else can do and to provide, in our case, provide a service to our users, our visiting scientists, that no other facility can provide, just like every other facility has that incentive. So we look for ways to find the right software interfaces where we can build up layers on a shared core. It's designed, therefore, to support this distributed collaboration with common components and then room to innovate and specialize and extend and replace. So I think that the takeaway from this slide is Tiled is part of a larger ecosystem that we are using along with a whole bunch of other software tools that may or may not be of general interest, but it can also be pulled out like any of these components and used alone. And we've seen as facilities join this collaboration, usually in a kind of a ground up way, they're grabbing one or two pieces that seem obviously useful to them, and then they may or may not start to use more and more of the pieces. We're avoiding being an all or nothing framework that you have to buy into entirely. So our current focus on the subject of this talk is data access for data science in this project that we're calling Tiled. We've been thinking about data access issues for several years. Tom Caswell and I, when we were graduate students, actually met creating PIMs for reading Python image sequences. And it has this general idea of, I don't want to have to care in my code how my data is stored. Some microscopes are writing special proprietary variants of TIFF. Other data sources are writing movie files, and we just want to think about these as NumPy-like objects in Python. That's the problem that PIMS was solving. At Brookhaven, we tried to generalize this in a project that we called Data Broker for separating the I/O code from the science code and trying to abstract away how the data happens to be stored from the structures that you're accessing in your code. In 2017, Anaconda started a similar project, a project with similar goals called Intake. When we found that, we decided to refactor Data Broker on top of it to try and get a broader reach and to understand what parts of the problem were general to the SciPy community and what parts were specific to us. We threw about 40 pull requests into Intake, mostly because its home is serving something on the scale of like 20 or maybe 100 CSV files, and our home is more like serving 10 to 100,000 scans done in an instrument. So it's a different scale, but it basically worked. We were really interested in this germ of an idea in Intake, of an intake server, of data as a service, rather than a Python library that has direct access to data and just abstracts out the I/O bits. What if you had something that could serve over HTTP or any kind of client service relationship? Intake had a germ of that idea in there. When we attempted to productionalize it, we found that the requirements of making that really work were in tension with other things that Intake wants to be, its other commitments. And so that basically led to Tiled, to starting fresh, taking what we learned from these other projects and making this new one. One of the goals of Tiled is to support search with extensible queries. So the kinds of search that we do are find me all the experiments where I was scanning these motors and maybe the temperature was below this value and it involved nickel, and further filter this by some range of months that I care about. This is pretty revolutionary stuff in synchrotron science. I like to say we're a decade or two behind the climate people and the astro people and the high energy people for just being stuck in traditional workflows and having code that manually extracts data from file names in a sort of disorganized way. So getting to this more database-like flow is a really big deal as our data scales up. We want to further standardize on structures and not formats. There's been a 40-year battle in synchrotron science to get people to standardize on one format, and we posit that will never succeed. There's never going to be one format that makes everyone happy. There's not even an optimal format for a given use case. Sometimes you need to store your data in more than one way to serve different access patterns and algorithms. But many tools do understand certain structures, your NumPy-like array, your ragged array, your tabular data, or hierarchies of these that may have a particular naming scheme and schema associated with them. These are not tied, of course, to any particular storage format or programming language. So we're trying to separate the idea of the structure embodied in, say, an HDF5 file or a netcdf file from the way it happens to be encoded at rest. If we can provide the data over a service as some appropriate format embodying the structure, then we, the people who are in charge of being the stewards of this data, can write it and store it however it makes sense given our hardware resources. So if we've got a vendor-provided detector that has a very opinionated data format that allows it to achieve its performance requirements, then we can just accept that. We write a reader for it, but we don't need to leak that weird format to the user. We can serve the user the data in some appropriate format that they request, like arrow, for example. And we can change our minds later about how it's stored and have transcoding pipelines or whatever we need without breaking the scientific analysis code. That's really the key goal, that the code should start with the structure, not start with IO. So to preview the demo a little bit, we can access tabular data as Apache Arrow, which is the Glasswire format for pandas and related libraries. We can then feed that directly into Xarray or pandas, working in sort of a data science flow. If we're integrating with tools that really need files, some closed source application or other existing application that needs the data in some inefficient or universal interchange format, we can request it that way from Tiled, and it can be transcoded on the fly or served from a cache. We can access.
Wait, Dan, you got a raised hand.
Oh, sorry. Thank you. Go ahead.
Oh, hey, yeah. I guess it was a minor thing, but I was wondering, I think it was back on slide 9. I was wondering if you could elaborate a bit on some of the requirements that, oh, not 9, 8? 7?
There you go.
It's the one where basically you said that the requirements for intake were sort of diverging from your needs. Yeah.
Yeah.
I wonder if you could elaborate on some of the other.
Sure. I think that intake is designed to be the end user application. It is not really designed to be a library for building larger applications. So if you look at the intake talks, it's usually demonstrated being used directly in a Jupyter notebook, for example. And some of the things that it's doing rely on saying yes to a lot of possible features and a lot of possible capabilities in a way that relies on the interfaces being a little bit loosely specified. I think that's Martin Durant is the lead intake developer, and he said intake is intentionally has these loosely specified interfaces that let you do very dynamic things in Python. So it's really optimized for, you've got a Python process with direct access to the data, and that's the thing that the user is using. If you try to build a service off of this, where you're, say, providing the client with information about the shapes and data types that it will receive, and then allowing the client to access the data chunk-wise, you need to have much more firmly specified interfaces for that inter-process communication to work. I think that's really the core issue.
Okay, so is it more of a layer thing? Like you would still maybe put intake on top of Tiled as a user interface?
I think you could, and I think you could. I'm hopeful that we don't have to totally split the ecosystem in half. So we're still going to the intake dev meetings, and we're talking about how you could do that. I
okay,
it's certainly
that
possible.
makes sense then. Yeah.
Cool. Okay, so yes, so I was showing that you can access the data in these efficient formats, which is what you'd want if you had a programmatic client, or you can access it in these universal formats, transcoded on the fly. For array data, similar story. By default, we just send C order buffers. The content you can feed directly to NumPy from buffer. But we could also serve TIFFs. We can also serve PNGs. And these are, of course, easy to extend. Where this gets fun then is you can request that Tiled serve just a subset of the data, a slice of an array, a subset of the columns in a table, or a subset of the partitions of its rows. This means that tiled will read as little as it can, which may be a little more than what you want, depending on what the file format can support, right? For example, HDF5, you can only read one chunk as the minimum amount, but it will certainly only send exactly what you want. So this opens up interesting possibilities for large longitudinal studies where you're training a model on, say, a large history of data, and you don't want all the data from every run, you want just a particular slice into it. This saves a lot of time. It's very different from the file-based model, where if you want, say, the first image in a time series or certain columns out of a table, you have to download the whole file before you can go in and address it structurally. So the server is doing a little more work here. It has to actually open the file. It's not just spooling opaque bytes to the client, but what you get for that is this structured semantic addressing of the data inside the total data set. So of course, this integrates naturally with Dask, and I'll show that in the demo, and then you can feed data directly into these other libraries. And so what this amounts to is Dask arrays and data frames wrap arbitrary Python callables. And in our case, they can wrap callables that are making authenticated HTTP requests to a tiled server and obtaining the chunk that way, rather than obtaining the chunk by, say, reading data directly out of a file that it can see. And once you have a service, there are all kinds of standard useful things you want to do with it. We're implementing modern web security standards, heavily inspired by how Jupyter and Jupyter Hub do this. You bring your own user management system. We have the beginnings of a set of authenticators that are very similar to Jupyter Hub authenticators. So you can authenticate based on your local system using PAM. We're working on integration with Globus and Orchid and other OAuth-based systems. Then you get granular access control enforcement. You can have access control per node in this tree of data sets, basically. And then you can, if you've got a service, do clever things on the service side to make sure that popular data sets are stored hot, and other performance optimization tricks. You can do local client-side caching. So just like with a web browser, if you load the same resource twice, you can check with the server to say, here's a hash of the content of this resource. Has it changed since the last time I got it? And the server can say yes or no. We could also do a sort of airplane mode that I'll demo, where you use a local cache entirely and just work completely offline. So I want to talk about what we have and what we sort of have and what we dream of, so it's clear what the status of this project is. So we have trees representing catalogs of data, you might say. These could be backed by files on disk, where it's just a direct mapping to a directory tree. These could be mapped by mapped to databases mediated through some Python code. I'll show an example of that. Or just totally fabricated in Python, and I'll show an example of that. We support array, data frame, and the various X-array structures, variable data array and data set. We're integrated with Dask. We have some nice configuration on the server and the client side to make this fairly easy to stand up. We have some CLIs to start the server and to do some convenient things on the client. We have serialization in several formats that I mentioned in passing earlier, and some documentation on how to register user-defined ones. And our docs are pretty good. We did this in a very documentation-driven development based process. So things that we have working, but you probably wouldn't have to try too hard to find some bugs in them. Basic shared secret authentication, just like if you type Jupyter Notebook and it generates a token on the fly. This OAuth 2 based authentication, I think this is pretty solid. This lets you have this sort of interaction where you authenticate once and then a token is stored in some persistent storage in a browser or on disk in Python, and you don't need to re-authenticate every time you use it, basically. We've played around with horizontal scaling and shown that we can run this with multiple processes. We haven't gone too far down that road. It's not documented, but it does basically work. I mentioned we have some client-side caching, and we can also, as I'll show in the demo, account for additional semantics on those core structures. So we can say, this is not just any opaque data frame. we know this is a data frame that the client can expect has certain columns with certain names, or this is not just any tree structure of data. This is the tree structure that has a certain specified layout that is netcdf, that is a certain flavor of Nexus, and so on. And we'll see in the demo how we can leverage that information. Then things we dream of, we really love integration with awkward array. We want to have first-class support for sparse arrays. We'd like the client to be able to request a downsampled view of arrays, which are so-called image pyramids. When we know something special about a structure, when we know it's a data frame with certain columns or a tree with a certain schema underneath it, then we can implement fast paths to batch requests that more efficiently access that data. So we want to push on that a little more. Dylan and a postdoc are working on the idea of a GraphQL endpoint to support more complex search queries than you can do with basic GET requests. We're looking at storage formats and compatibility with things like Caterva and Czar. And finally, currently tiled is for read-only clients. I want to be clear that the data underneath a tiled server is allowed to change. So if it's a database, records can be updated or added. If it's a file system, files can appear to be removed. That's fine. All the caching and stuff knows how to deal with that. But the client is not allowed currently to initiate a change like that, not allowed to submit data sets that then get added to the tiled server. That's something we'd like to add likely in the fall. So with that, I'll do a demo and collect any questions that might have accumulated. So let me take a breath. Are there any questions or thoughts at this point?
So the GraphQL looked, I hadn't given that as a thought as an add-on. Is that is that something where you're going to have to implement your own backend to process queries like that? And GraphQL is a fairly complete query language.
I'm going to forward that to Dylan if you're game.
Yeah, I'm not 100% sure I get the gist of the question, but let me try and see if I got close. Yes, there will have to be a server implementation, and hopefully working on some stable third-party codes to help that. I think most of the real development of the GraphQL implementation is identifying the schema that you publish, and then making sure it's implementable. Does that answer? I think, yeah. Sorry, let me actually also say that, and unfortunately I have to go at 9:30 here. There is a search mechanism in tiled today, and since tiled is slightly RESTful, more JSON API, you can do as much as you feel like implementing in URLs for search querying, but it just feels like there's a limit to how complicated you can make a query that you send just through a URL and how complicated you can publish what you support. We like GraphQL because of the publishability of the schema. That's a big part of it. So we can really tell implementers what's available for searching. Did I get close?
Yeah.
And if I can pipe in one other comment, this is something Dan was pushing on when we were talking about prep for this talk, is that the search part can be fully decoupled from the data access part. Because if you have a search service that just provides the right URLs into tiled, that can be done in an entirely separate service.
Yeah, I could imagine a future where this becomes
right.
two different microservices, one for search and one for just this chunk-based access to data. Yeah. On the other hand, it's convenient to build them together right now. So we'll see where that goes.
Okay.
Yeah, and if they are separated, I'm sure there's a fair amount of tiled code that would be shared between the two.
Mm-hmm. Yes.
And there's a comment in chat along these lines. It's from Ben. So the search says which files you get, not which rows from a file. This was basically where I was going to go next.
Currently, it's finding you nodes in a tree, and you cannot search within. Once you've got to a data frame or an array, you can no
Right.
longer search inside that. But there's no reason that we couldn't implement that. We just haven't. We don't.
Well,
use that.
your idea, the thing that you proposed, what was it, the pyramid image? I can't remember the name exactly.
Yep.
So that's something that's already starting to summarize, at least if I understood that properly, it would be some algorithm you'd run that would summarize the data and return that. And that summarization step is basically a query of one sort or another, if you want to just generalize that idea.
Yes.
Um,
Yes, I want to think carefully about, I think that's completely right. And also I want to think carefully about avoiding turning this into an RPC data reduction service. I want to keep it just at IO. It could be part of a microservice deployment that also does some data reduction. I think pyramid is just downsampling, so you can justify that as a kind of data access that is a pretty important use case for image people. But I wouldn't want to go too far beyond filtering.
Sure.
Yep.
Agreed.
Okay, I might jump into demo time then, unless there's anything else on somebody's mind. So this is one way to start a tiled server is to give it a Python object, the path to a Python object that implements this expected API. This is a tree that contains some data sets, 2 arrays, A and B, and a data frame C. So this is just to show you what this looks like. This data is clearly, as you can see, being generated on the fly. It could be read eagerly or lazily from somewhere else. Could be a file, could be a database, could be a mixture of the two, right? It's just a Python object. So let's tiled serve PyObject tiled examples generated minimal, and then colon the name of the object, which in this case is tree. I'm going to turn off access controls for this demo, so -- public, and server comes up. Over here, one thing we can do is just curl that. So curl boom. That's not very readable, so I'm going to use HTTP, which is a more modern alternative to curl that gives us color coding and other nice things. So the root route just tells us about the different structures, data frame, and how we're allowed to ask for the data. This again is coming from a user extensible registry. And if a nice place to start would be what are the entries in this root level tree, and it tells us a lot of information about the entries. So I'll focus down on just one. It says this is a data set called A. It's an array. This is the so-called microstructure, the things that are opaque to the server but important to the client to be able to unpack this into a NumPy array. And it tells us the shape, and if there were internal chunking, there could be multiple chunks per axis. This is just like Dask, but it doesn't necessarily have to involve Dask specifically. And then we have links to where we can go and grab this data. So the simplest thing we could do is grab this full link. So I'll punch that in here. We're saying this is very much like GitHub URLs, right? This is the verb and the rest is the noun. Get me the full array for this this node A. And that gives it to me as a C-ordered buffer that I could feed to NumPy by default, but I can ask for it in any format that I want, like text, CSV. And by the way, the metadata that we were getting here came to us in JSON, but we could also ask for that more efficiently in application message pack. And that's what the Python client will do. So that's binary, more compact, more fast. If I now want to do this from the Python client, I can start IPython, import the tiled client, connect up to this URI, and now I've got a Python object that is making requests against the server. We can see it just hit this endpoint here. I'll put some space in the log so we can see what it does next. If I ask it about A, it tells me that's an array client. That was a little bit slow. We're very careful about deferring the imports until we need them. And what that did was import NumPy for the first time. So if I do that a second time, it's fast. And you can see that's asking for A. There's where A fits into that URL encoded URL. And if I grab that, that gives me the whole NumPy array, which hit the array block route. This is more sophisticated than array full. This lets us ask for multiple blocks of the array in parallel if it has multiple chunks. And in this case, it just needed block 0, 0. We can do basic slicing on this, and that will grab just the data that it needs to give me a subset of the array. Now I'm going to go back to my server, and I'm going to start a larger example so we can see how some of that internal chunking works. So this is taking some time to generate. I think the largest data set in here is 800 gigs. There we go, we're up. Come back over here, I'll connect afresh. And now we can see a whole bunch of stuff in here. This object, by the way, is designed to be as familiar as possible. It implements the dictionary interface, the mapping interface in Python, which we can confirm like that. So I can list it, I can look at the items in it, for example. There's also a utility, from tiled utils import tree that simulates the Unix tree command and shows me everything that's in here. So I've got a very nested catalog with example data of different sizes. This is nice for development and demos like this one. If I go into, for example, C arrays, that's another tree, a node in the tree with some arrays under it. And if I look at the entry medium, now we're down to a leaf that has an array in it. I could load the medium array. Let's put some space in the server logs again and now load the large array. This is large enough that tiled is chunking it. And so you can see requests coming in for blocks with different indexes here in the server log. And these are requested by Dask workers on the client side that are making these requests in parallel. And here our array came down. We can put Dask a little more forward here if we tell it that we want the objects that represent these data sets and that ultimately are responsible for requesting the chunks and putting them together to use Dask and to give us Dask objects. So now if I make the same request, I have a Dask array client, and that will give me a Dask array. As I said when I was going through the slides, this is just a Dask array. There's nothing childish about this, but the functions wrapped inside the Dask tasks happen to make authenticated HTTP requests against the tiled server rather than loading directly data directly out of a file or something more standard for Dask. But from Dask's point of view, this is just normal stuff. And what's interesting about this is I could do, say, a sub-slice like this, where now I've got a 10 by 10 subarray, and let's put space on the server logs again. If I compute that, just naturally, it only asks for the specific block that it needs. So we left tiled at this point behind as far as the outward-facing user API goes, and we knew that we were potentially going to grab the whole data set. But then when we down select that somewhere in our computational algorithm, we end up only pulling the data that we actually need. Now let's do some stuff with search. So here's my catalog again. I'm going to import.
Actually, a couple questions about the.
Yeah, go ahead.
So the client, you said you use Dask behind the scenes always to sort of parallelize what you're doing. Is that true?
That's correct. The NumPy array client just uses the Dask client and calls compute for you, basically. It wouldn't have to.
Okay, and so if you haven't hooked up, a cluster to it, it just sort of spins up its own little, like.
Right, it does the natural Dask thing where I think it's using a thread-based scheduler on
Okay.
the client side
Yeah.
if there's no cluster hooked up.
And then when you said it forms the Dask tasks using just HTTP request, does that mean that it's using the Python standard library to do the requests? Or do you need the tiled library installed on all the workers to execute those requests?
That's a good question. It's using HTTPX rather than the built-in.
Right, because you like async.
The Python built-in. Yeah, and we have been really taking our cue from Dask. We've been really aggressive about minimizing the dependencies that the client needs. So I think you can install tiled. If you pip install tiled client, you need maybe just HTTPX and maybe one or two other very small things. But it's quite light. And so if you only need NumPy if you're actually materializing NumPy arrays, you only need pandas if you need data frames. Same for Xarray. So installing that on all the workers and importing it on the workers should be fairly light.
Okay.
Anything else about the Dask stuff while we're here?
That's all I had.
All right, I'll do some search. Oops. Got to get my fingers in the right place. There we go. So search queries and tiled are data classes. They're just descriptive objects, just characterizing the query with no information about how to actually do it. So if we look at the full source code of this full text query, it's just two pieces of state. What text are we searching for, and are we case sensitive or not? It's on the server side that we have to deal with, is this backed by a Mongo database with a text index? Is this backed by a directory of files? Is this backed by a Python object in memory? And then implement how to do that query on that particular backend. And perhaps not all queries are suitable for all backends. That's fine. Let's do, I think I have a nested catalog in here with some metadata on it. So I can search for full text cat. Which of these nodes in the tree has metadata with the word cat in it? And it turns out that the small one has metadata with the word cat, as indeed we can confirm. If we just look at the small metadata. Metadata sits alongside the content, like an XML attribute sits alongside its content, or like an HDF5 group attribute sits alongside its content. So this is a pretty generic feature of a lot of systems that we want to model in tiled, and that's why it's there. We can see cat was in there, and a nice idea that we borrowed from intake here is that the result of a search is the same type. It's just another node. And so that allows you to nest searches in this way, where I can say, okay, now, this is a little bit silly because there's only one result, but you can see if I search for banana, I get the result back. But if I search for something that's not there, the result is an empty catalog. So that's how search works in the Python API. The server is getting these filter, full text, condition, case sensitive, blah, 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 blah. And this is what Dylan was getting at of there gets to be a point where it's not reasonable to encode these things in URLs. I guess you don't really care how pretty the URLs are, but it becomes hard to advertise what is allowed and how these things compose at a certain point. An advantage of doing this with GET is that standard caching mechanisms are very happy with this. But when you graduate to a certain point of complexity, basically when your queries have queries, when you're trying to nest queries, doing something like an OR, a logical OR in the simplest case, or more complex things than that, you start to want to get to post and to the world of GraphQL to express those things. I'm going to switch what I'm sharing now to go to my web browser and show what it looks like to hit this from a web browser. I'm going to rejuggle a little bit to fix the aspect ratio. Hopefully that's okay. So if I go to localhost 8000, we see the same thing we saw in the console earlier, sort of basic information about the server. This has auto-generated OpenAPI docs, where we can see all the different routes, and you can even play with this interactively and make requests. That's a nice thing we get for free from the Fast API framework on which this is built. But I'll just type a URL manually here to get something. So I'm going to say, give me array full, the medium array. Oh, that's under a node called arrays. So there's my image. The browser requests HTML by default, and the server happily complies by placing a PNG image in a web page. I could ask for it differently. I could say format equals image PNG, or if I don't know what a MIME type is, oops, wait, format equals image PNG. That gave me a PNG directly. If I've never heard of a MIME type, I might be happier to just type format equals PNG, and it resolves what that means. But maybe more interestingly, I can also slice this in the browser. So I could say slice equals :10, for example. I have to spell it right. There you go. And that could be a multi-dimensional slice, say comma 20 through 50. Normal NumPy-ish syntax there.
If you add another colon, do you get downsampling?
I forget if I implemented that. Let's find out. Yes, I think you do. Let me do it bigger so we can really see. So ::2, ::4. Huh. Yeah. Great.
Nice.
We implement pyramids already. Cool. Yeah. All right. Let's do.
Well, decimation pyramids, not averaging pyramids.
Yeah. No, that's true. That's true. Okay. Here's the data frame route. Again, browsers request HTML, and we're happy to comply. But if you want it as CSV or something, we can do that too. It just downloaded a CSV. And then here the semantics are a little different, right? According to the structure of data frame, you cannot do arbitrary slices into a Dask data frame, and nor can you do it into this data frame for the same reason. But you can ask for subsets of the columns. So column equals A, and column equals B. Oops, B. There we go, for example. And if I go back, you can't see what I'm typing now. I'm going to knock my server over. I'm going to grab one of our tutorials and copy this invocation and start the server like that. Here I'm allowing requests to come in from applications served from Plotly's Chart Studio. So here's Plotly Chart Studio. I can go chart, import by URL, copy this URL back to Plotly, and I need to tell it format equals CSV, and that just hit my server, grabbed columns A and B as CSV, and then you can do whatever you want to do in Plotly. So I think this is a nice example of the power of doing your data access via a service, where you can give it to whatever client in whatever format is appropriate to that structure, letting it do slicing that's based on the structure of the data. Has a lot of advantages over file-based workflows. Second to last thing I want to show is going back to the terminal. Oh, I see chats. Jim asks, if the text of two queries would perform equivalent operations, maybe this should be normalized to a standard form before being converted into URLs. Yeah, I agree. There's another place where we need to be doing something like that. The caches, which I'll show in a moment, could also do to be smart about that. So that if you've cached something and then you make a request that's technically equivalent, we want the cache to recognize that we have cached that result. That's a good thought. Okay, so resharing my terminal now and moving some things around to get the aspect ratios right. Can someone just holler that you can see my terminal?
Yes.
Great, thanks. I've got some example files in this directory called example files. It's got some nested structure, so I'll use the Unix utility tree to show that. I've got some CSVs, some TIFFs, an Excel file in there. I'm going to do tiled serve directory, which is just a shorthand for a specific Python object that walks a directory tree and then watches it on a thread to see if files get added or removed, and translates that into a structure that the tiled server can understand. That Oh, that ran with access control, and I don't want to do that. So I'm going to say public. And I'm going to come back over here. I'm going to reconnect. And now I've got this Python side representation of this directory structure. The names just came from the file names, but they wouldn't have to. I can go into a subdirectory, and that looks like a node. I can grab a file like d.tiff, and that's an array, and I could access its data, right, without having to know it's a tiff. And to emphasize the point, tiff file is not installed, wouldn't have to be installed in this Python environment. It's just receiving the bytes as C-ordered buffers. Now let's play with some caching on this. I can say tiled client cache and make a cache in memory. Say it can have up to 2 gigabytes, and then define my client like this. And if I access this the first time and check the server logs, everything looks green and normal. If I access it a second time, we see 304 not modified, which means the client included in its request a hash that the server gave it originally the first time it asked for that data, and asked the server, if this hasn't changed, then don't bother sending a payload. If it had changed, then the server would have the opportunity to tell us that. Let's look at what happens if I want to take the whole, basically want to walk this entire client, the entire tree, and make sure that I touch everything in it so that it all gets included in the cache. That's done. Now I could kill the server. That's no longer there. I could make an offline version of this catalog. This is just a way to basically reinit a copy of this object with different parameters. And now my offline catalog is perfectly happy to let me walk this. My online catalog will error out and say, connection refused or what have you. VS Code is taking its sweet time, lovingly color coding this trace back for me. That's great. Okay. But the offline catalog, I can dig in here and grab this data set. It obviously can't do novel searches for me, but it can do pretty much everything else. And if I had thought to perform any search that I care about while I was connected, those search results would be cached. So that's offline mode. Any questions about that? I should mention that I think I demoed a cache in memory, but you can also do a cache on disk where you give it some directory, and then you can kill the process, restart the process, and you have persistent storage as opposed to in-memory storage. Okay, I'm going to do some authentication stuff now. So we've used web standards for authentication, as I mentioned a couple times while starting this up. By default, it does exactly what Jupyter Notebook does. It generates this random key for a single session. You can configure that in a config file or with an environment variable if you want to fix what that is. And then someone trying to connect to this one now from Python or anything else will find that they get rejected if they do not have that API key in there, not authenticated, but with the proper URL. It'll let me in. That's the basic single user deployment. But we can have more interesting deployments, more in the mode of Jupyter Hub, where you have multiple users connected to one deployment, where you specify some access policy that says the general unauthenticated public can see part of this if you want. Alice can see these two things. Bob can see these two things. And Kara can see everything. Kara is like an admin in this system. This is a very brute force way to specify how access works. It's not the way I would generally do this. You'd want to map this to something like a Unix group, Active Directory group, or something to do with your database. And there are interfaces that would do that efficiently. But this shows a general idea of what the scope of access control is. Then I make my my tree with these different entries in it. And oops, wait. In this toy example, it gets its password from these environment variables. So we could say Alice has a password and Bob has a password. This is in the docs. And now we've started up an authenticated server where I say I'm Alice and it says prove it. And now I can see what Alice can see. Alternatively, I could say I'm Bob. I mistyped that password, I bet. There we go. And now I can see a different set of things that Bob is allowed to see. This is using so-called sliding sessions, which I sort of tripped over trying to explain in the slides. But the idea is that you are challenged to refresh your session, and as long as you've used it, as long as you've used your authentication recently, it continues to renew. This is like how the GitHub command line client works, I think. So it's a fairly nice user experience already. The last thing I want to show is connecting up to one of these deployments that takes advantage of what we're calling a spec, to say this is not just any tree of data that you have to opaquely walk to know what's in it, but it's a particular tree that follows a particular specification. The client then can do things like give you nice rippers or extra convenience methods, or use this to get extra performance out of a system. So here we have some example data from our synchrotron. This BMM is the name of a particular instrument at the synchrotron, and these are 123 scans that were done of that instrument. The repr that we're getting for this object has scan IDs in it, because that's a useful thing to show in this case. The object that you get back has a special type that came from a totally different library, not tiled. And using Python entry points, we can do this in a distributed way. So tiled doesn't have to know about your third-party integration to operate with it. It comes down, the server tells the client in the JSON that it gets back, if you care, this implements catalog of Blue Sky Run's spec. If the tiled client doesn't have the right software to know what that is, it just degrades and gives you a basic client. But if it does recognize this, it can give you a special client object with, as I say, special performance and usability methods to give a better user experience. So we'll drill into this a little bit just to see what this looks like for us. If I look at a particular scan by its ID, I see this has like some nodes inside it, scan ID, when the scan was done, all things that are convenient for us, but make assumptions about the content of the data that are not generally true for all data. And I can grab what we call an event stream here, which also has its own particular type and structure. And finally, I get down to a standard Xarray data set, which I can access all of. And now we've left tiled, we've left our particular stuff, and we have the data in a familiar object. So that concludes the demo. And we've only 3 minutes left to keep chatting on the clock, but I'm happy to hang out for longer if people have more than 3 minutes of conversation.
Daniel, thanks. Came back.
Sure.
But thanks a lot. That was really good. Are other people have questions or want to see further things in the demo?
I guess I might revisit my intake question and ask if some of the UIs you get with intake are sort of integrated with this in like Jupyter and stuff, or if that makes sense even.
I think it does. I'm just trying to think how to formulate this. So you're talking about like the intake Jupyter GUI?
Yeah, like just to like click and browse data sets and stuff.
Yeah, I think that should work. That should work quite well with this. I think all you would need is a little bit of an adapter between our client-side objects and intakes objects, but they share a bunch of DNA. So I think you could do that easily enough. Oh, there's something else in the chat here.
Yeah, I'd put as
That's
suggestion
neat. I didn't
for,
know about UHI.
well, there's something made for a histogram library that was developed by IRIS-HEP. It's kind of a neat idea just to use the third item in the slice as a reducer optionally with a magic object. So you can imagine using like, instead of, you imagine averaging or, you know, kernel filters, reducers to do the downsampling.
That's really clever. This is boost histogram that you refer to?
Yeah, well, the Python library on top of it.
Specifically, it's hist. In case you're looking at the Python boost histogram, there's another library, hist, which subclasses it.
I see.
Yeah, so
Cool.
HIST.
So one question I have for the people here is, when we try to add awkward array to this, do you think it will fit comfortably next to these other structures that we have of data frame, array, and the X array things, which are sort of nested? Or is that going to prompt a deeper rethinking of what a structure means and how these things fit together?
It might involve, it might be part of the work involved in making an awkward collection type in Dask. So I can tell you now that the structures in awkward array do not fit comfortably in a Dask array. And you would lose a lot of functionality if you made it a Dask bag. So we are, so actually we have a formal project planned with Anaconda to develop an awkward collection in Dask. So it would be, you know, a new collection type. I don't know how easy or hard that would be to integrate into what you're doing, because it seems like, you know, since you're relying on Dask to provide the abstraction, then that shouldn't be too hard, because it would just be yet another collection, you know, distinct from array, data frame, bag.
Right. I don't think we would necessarily have to wait for that, even though it does seem like that once that's ready, that would be a good way to go.
Yeah, you already do arrow, right, as a delivery mechanism.
Yeah.
And certainly jagged arrays will fit into an arrow description. The one thing, if I understand correctly right now, is that basically, is it correct that any data can be represented in any of the output forms, or are there already limitations or incompatibilities that you have to track?
Well, there's a registry of structures to output formats. So, you know, let's say data frame can go to arrow, but an X-array data set, I don't believe fits an arrow. Or an image can go to PNG, but it doesn't really make a lot of sense to export a data frame as PNG. A data frame can go to Excel, but an array doesn't go to Excel. So that's the limitation.
But you know, if you've got that already, then it would be that, you know, until Dask had baked in support for awkward, you just would have to leave that entry blank. However, you know, going to arrow for, you know, importing something to ship it over the wire would make a lot of sense.
Yeah, I think that's right.
In fact, I admit that would be a much shorter connection, because we have a 2 arrow from arrow, which are nearly 0 copy. So if you know, that would be just one last step in the process.
Right. Having very briefly looked at the tiled code, and by very briefly I mean I know enough to probably be dangerous, but not enough to actually do anything useful. It looked to me like the writing the loader for awkward wouldn't be that hard, because it could basically be copied from some of these other formats.
The hard part, I think, would be if we just want to treat a single awkward array as an opaque thing, then that's easy. But do we want to be able to address inside of it, similar to asking for a subslice of a NumPy array or a subset of the columns in a data frame? What's the analogy there, and how does that work? I think that's where this gets fun and maybe hard.
Yeah. That's what I
The-
was thinking too. You know,
The-
this some subset of the slicing is common, right?
Mhm.
All awkward arrays can simulate NumPy in their slicing syntax. There's this additional considerations for certain types of slices and column slices.
Maybe the question is just, it is the syntax that you query it rich enough to apply to awkward arrays? Do you actually need to do anything to the, you know, just basically copy over the slicing and hand it off to awkward and let awkward do all the work?
Yeah, that is the question, I think.
Well, would you want to support slices that have arrays in them? Because those slices can be large data objects.
Well, that wouldn't work with get.
Yeah, I would just start with a no. You know, you start simple and then understand how it's used and then see what it would take to build it.
Okay, but it sounds like getting an MVP build on awkward is sort of fairly straightforward. We can just support the basic slicing we support now, which does explicitly not support lists of positions, but does support what you've seen, and then see what's missing.
Yeah.
I guess the one would be column slicing using a string in the get item fields.
Would it be the union of what data frames let you do and what arrays let you do then, in a sense? Because with data frames we have like columns equals, and with arrays we have slice equals. Is it both for awkward?
Yeah, pretty much. You can either, basically there's this sort of implied justification, right? You know, you can, for a given depth of nested arrays, if there's records in there, you just have to you know, choose the appropriate record slice, which is sort of like a column slice, and then the appropriate row slice, which is more along the lines of a NumPy, like, you know, slice. So yeah, it is kind of both, but it does depend on the order of which you slice, which ones would be available at a given depth.
Like where you are in the tree. Yeah.
Right.
It's similar to since advanced slicing, to using NumPy's definition of advanced slicing. Since advanced slicing is off the table, we're talking about basic slicing. So that means slice objects, integers, and strings. It's like slicing a structured array in NumPy, where you can use a string to pick out one column, and then you can use an integer to pick out one row, or a slice to pick out some rows, or a list of strings to pick out some columns. So then in the two-dimensional thing, you can cut one or multiple. The difference with awkward arrays is that, so in a structured array, the string slicing and the integer or slice slicing have to be different slices. They have to be in different square brackets. In an awkward array, they can be in a tuple, and you can have multiple strings in the tuple for records inside of records. Just as you can have multiple integers and slice objects in a tuple for multiple dimensions in a multi-dimensional array. So that is the scope of slices, basic slices.
I think we have to think carefully about, you know, we have this idea of a tree object, which we're using to map directories and HDF5 files and similar. I want to make sure that there's not a weird disconnect between records and inside records in awkward array and nodes inside trees in our thing. When you cross between a directory and an HDF5 file, you don't feel the difference. So if you've got two similar structures inside subgroups of an HDF5 file, or two separate HDF5 files with those structures at top level, the tiled client cannot see the difference. And does it make sense to say something similar should be happening with awkward array record inside records?
Now, I think that this slicing is distinct from the tree navigation you're talking about. The tree navigation is kind of like navigating the objects, the groups and data sets in a HDF5 file, which is distinct from slicing a data set. With awkward arrays, the records inside a data set are like, well, the field slicing of records inside an awkward array is like slicing up a data set. So for instance, the two fields of a record, two columns, the individual rows correspond. Whereas if you had two strings for two different data sets in an HDF5 file, they don't have to be the same length, and the items have no relationship to each other, it's separate tables. So I think that this kind of slicing, even though it does involve both strings and numbers and slices, is distinct from the finding a group data set in an HDF5-like tree.
And hence it's arrow compatible, whereas an arbitrary HDF5 tree structure would not. That makes sense.
Yeah. Yeah.
So an idea Dan and I have been talking about is that, if you just like squint and say like all these things, this is all just trees of arrays and it's all just groups, it's all the way down. But that there's really common patterns that have these relationships, like these must be the same length. I know I'm going to have 4 of these or whatever, that are common enough that we have like high performance, like implementation level data structures on them. And so you kind of have on one side, you've got semantics coming down from the top, and you've got performance like data structures coming up from the bottom. And if you're only looking at arrays, they never meet. But when you get to data frames and awkward arrays, the semantics go down and the performance goes up, and you get these weird middle cases where you can tie yourself in knots. Like, is this semantic only or is this performance only? And there's something interesting there. I'm not sure what the answer is, but there's something interesting there.
Great. Well, maybe we should wrap then, as we're over time. Does anyone else want to speak up with any opportunities you think that we're missing, or other related work that we should keep our eye on before we close?
I guess I have one question for the IRIS folks. I know I've been seeing you're working on a bunch of like computation as a service tools. Would this sort of API make sense as a front end for that?
It looks like it, although Gordon is the one to ask about that, and he just left. This is looking a lot like parts of Service X, not the whole of Service X. So it's looking like there's a lot of opportunity for sharing here.
Cool.
It's looking very good, yeah. I think that Service X, I'm speaking for him, hasn't explored how users navigate the data that's there. I think they've been focusing on the problems of data format conversion, which I think plugs, the working parts of this and the working parts of that plug together very nicely.
Sounds that way. If data format conversion, meaning that the transcoding step, data is stored like X but needs to be served like Y?
Yeah, data in, not just in root files, but in custom root files that apply corrections as you read them, stuff like that. So they've been writing transformer plugins that use the code that people have been writing, but they usually write it downstream, at the place where they've downloaded the files, and doing that in a service to provide just Apache Arrow views of the data.
Cool, that makes sense.
Personally, I'd be interested in looking at the different backends that you've implemented and what kind of shared abstractions you've seen with them. Is there some documentation on the different backends that you've sort of built? And because it sounds like as a new user to this service, you have to walk in the door and figure out how to make the backend for your ecosystem, right?
Yeah, I think that's right. So the implementations that exist right now are in memory, this file walking thing, and the one that's in what we call Data Broker that's integrated with MongoDB plus external files that have large arrays in it. I don't think I'm far enough along to have anything coherent to say about what it might look like to integrate with other sophisticated backends. But one thing I'd like to do is maybe implement Tiled as a cache layer for services like Globus, or a toy example of this that I thought of putting in the docs is a cache layer for astronomy picture of the day, where you don't have to know, the format, and it can keep a hot copy and it can downsample it on demand or ahead of time. I think once we start building that in, we're going to see shared patterns around caching on the server side, which we have a little bit of, but it sort of happens at the implementation particulars. It doesn't work its way up into the core yet, and perhaps some shared patterns around some intermediate representation that lets you implement the search the searches in a way that's shared. But that's a very rough thought that maybe I can't elaborate on. So that's the state of things right now. Maybe I'll look at adding a section to the docs on what I have so far.
Yeah, well, and I guess you mentioned integrating with ZAR, which would, correct me if I'm wrong, would be another example of a kind of backend, right?
Absolutely, and it could actually be ZAR on the back end and on the front end, right? I want to be able to read from a ZAR backend and serve it as tiled, but I also want to be to read from whatever and pretend to be ZAR, have a /ZAR endpoint from which the URLs below that look like things that ZAR wants. That's something that Martin Durant from Intake suggested and may help us push on.
Cool.
Yeah. All right then. I'm, as always, happy to keep hanging out, but I don't want to take more people's time. So keep in touch. Very good.
Yeah, thank you. This is
Thank you.
very interesting.
Cool. Thanks again, everyone.